Hello, everybody, and welcome to this new IRENA seminar. I'm very happy today to introduce you Alice Manna, who is a young researcher and a collaborator of the NTOF collaboration. NTOF is an experiment at CERN, which is dedicated to the measurement of neutron-induced reaction cross-section. And actually today, Alice will present us one of the recent results from NTOF. So Alice, you have 45 minutes, and we can leave all the questions at the end. So please, you can start.
Okay, so I guess you're seeing my screen with nothing in the middle, I hope. So thank you, Denise. I'm Alice Manna, and as you say, I'm a postdoc, and I'm working in NTOF facility at CERN. I will talk about the fission cross-section of uranium-235 in the high energy region. I can imagine that is not a common topic for this kind of seminar, but we will see that there is an importance also for the astrophysics group, the fission cross-section. So why we are still talking about fission? I mean, as you know, the fission is a reaction that is studied since 67 years ago, and is super well known, but still there are some open questions and some part of the reaction that are not really known, especially if we go in the high energy region. Means that when the projectile that induces the fission reaction is kind of from 100 MeV and or higher, it starts some dynamic effect that still are under investigated. Also because from a collective reaction, we are going to a single particle process. So this is still important for the theoretical point of view. Or, for example, the effect of the isospin. So to understand if a neutron that induces a fission reaction or a protons, we have at the end the same property of the reaction itself. Always in the high energy region, because below we have the barrier, so it cannot be the same. But still, the fission reaction cross-section is still important also for other, for example, application as the reactor technology or the dosimetry, but also for nuclear astrophysics. So when we talk about fission and the astrophysics environment is the air process environment. So I guess all of you know we are talking about an environment with a high neutron density and high temperature. So what happened is that the nuclei, the probability to capture a neutron is higher than the probability to beta decay. So this means that we are going to populate in this environment, thanks to the air process, this part of the nuclear char that is far from the stability, the value of stability that is here in black. And we produce this exotic, super exotic nuclei, and we go higher in the mass up to about 280 when we have the closure of the neutron shell. So this means that the probability to capture again another neutron is lower to beta decay, and in this super high mass nuclei, it starts to play a role the fission reaction. So this high nuclei can go through fission, as I say, and the fission fragment produced in general in the fission reaction are not symmetric. What do you mean? What I mean, in the sense that this is an example. If we take, for example, the americium that we know that we measure, you can see the mass distribution of the fission fragment coming from the americium is not symmetric, because we have a fission fragment for which the mass number coincides. So is where we have a closer shell for neutrons, means that we have in the in a region in which we have a magic number for neutron for both the fission fragment. This is why we have these two peaks in the mass distribution of the fission fragment. So if we go back to this chart of nuclei coming from this high mass nuclei, we go to fission. So this means that we are going to populate again this region with a neutron number that is around 80, and this region with a neutron number that is around 30. And so we can restart again their process and so on. And this consecutive air process and fission recycling can happen something like 2 or 3 or 4 times until when the temperature in the environment is high enough to keep it going. There are some proof that the fission recycling plays a role in the nucleosynthesis, because, for example, here in this plot we have the abundance, the solar abundance coming from the air process. So this means that taking from the total abundance, we subtract the slow process component. So in the end, we have only the abundance coming from the S process. And in the same plot, we can see one model, but you can see 2 curves. They're green and the blue one. The main difference between the two is that in the green one, we are trying to reproduce the abundance of the solar system without taking account this fission process. And in the blue one is when the model taking account also this effect. As you can see here, introducing the fission process, we are able to reproduce better the experimental abundance of our solar system. But as I say, the air process is able to populate these super exotic nuclei. This means that study a fission reaction in a laboratory, for example, of this kind of nuclei is a kind of impossible. The only thing that we can do to increase our knowledge and to increase the knowledge related to this fission recycling process is to increase the accuracy and to try to know as much as possible what we can know about the fission process, in order to have a fission model that is able to reproduce as better as he can the process itself, and so is also able to reproduce something that we can not measure in our laboratory. So this means that we need more experimental data set. This is just for example. If we take the example of the uranium-235, that, as you know for sure, is one of the most important fission cross-section, that is well known in the sense that, for example, in the energy range from 150 keV to 200 MeV, when I talk about energy, I talk about neutron energy, so the energy of the projectile that induced the fission reaction. So in this wide energy range, this fission cross-section is known with an uncertainty that is around 1%. And this is why it's also defined as a standard cross-section. But for example, if we go in this energy region that is reported here in this plot, so from 10 MeV to 200 MeV, you can see that here there are only 2 experimental data sets. And until when you have data, all the models agree and everything is perfect. But then from 200 MeV, there are no any more experimental data. There are only theoretical calculation. And this is just to show you how, without the improvement of the theoretical model for the fission reaction, we are not able to reproduce the fission cross-section, because as you can see here, I report 3 different calculations, and all of them disagree each other. So we need to know with more accuracy and with more precision, and to try to expand as much as possible the information that we can have about this process in order to be able to predict as better as possible what we cannot measure in our lab. As I say, I will talk about the fission cross-section in the high energy region, because as you have seen, there are no experimental data from 200 MeV. So our idea was to try to measure this fission cross-section. And then TOF is the Neutron time-of-flight facility at CERN, and is one of the few facilities in the world in which this kind of measurement can be done, because first of all, you need neutron, high energy neutron, that are not super easy to find them. So the neutron time-of-flight facility, as I say, is at CERN, and the idea is to use the protons that are accelerating from the PS, from the proton synchrotron, and they impinge to a LED spallation target. And from the LED spallation target, we have a lot of particles, and we have also the neutrons. So if we go to zoom in our line, here you see we have the protons that reach our spallation target, and now we have 3 different experimental areas. One of the 3 is called near, that is placed at 3 meters far away from the spallation target, and we use MeV for activation measurement. And we have 2 other experimental areas in which we perform time-of-flight measurement, that is year 1 and year 2. Year 2 is placed in vertical line 20 meters far away from the LED spallation target, and year 1 at about 200 meters from the spallation target. In the 2 lines, both of them, we have a magnet and 2 collimators in order to select only the neutron that are able to reach the experimental area, and in order to have a beam profile focus and define in the 2 areas. So the main characteristic of the NTOF facility regarding the 2 time-of-flight experimental area is that we have a high energy resolution. This is thanks to the time-of-flight technique that we use, and thanks to the long flight path, especially for year 1. The second important feature is the high neutron flux that expands in the high energy range. This is thanks to the spallation reaction that we use to produce the neutrons, and to the spallation target, and the energy the protons that impinge in the spallation target. So as you can see, from each proton we produce 350 neutrons. And here in this plot, you can see the neutron flux per bunch. And here in red, there is the year 1 neutron flux that, as you can see, can reach 1 GeV of neutron energy. And since year 2 is closer to the spallation target, we have higher flux, but it also finishes a bit before in energy because it's in the vertical and on the horizontal line. So now we'll do a small focus in the time of flight technique. So as I say, we use a protons accelerate from the PS. So we have a pulsed proton beam that impinge in our neutron target. So thanks to our magnet in the end, in our line, we have gammas and neutrons. And as you can see here, if you leave the space to the particle fly, we will have a good separation between the gammas rays and the neutrons, especially the high energy neutrons that will arrive early, I mean, as soon later than the gamma, and the low energy neutrons that are in time later on with respect to the high energy neutrons. So this is just a couple of formula just to understand a bit better. So if we take our time of flight, means that our is the subtraction between our stop, that the stop is when the neutron arrive in the experimental area and we detect an event, minus the time in which the neutrons are generating the spallation target. So thanks to that, we have the velocity and so the energy of the neutron that produce the reaction that we are seeing. As you can see here, the energy resolution is related to the time of flight resolution, so the time resolution, and the length of our flight path, so the length of that our neutron has to travel. If this length is long, as for example year 1 with about 200 meters, this is completely negligible. So we have, this is why we have a nice energy resolution. From the beginning, at MTOF, we perform several measurements. This is a kind of recap of all of them. The main reaction that we are investigating are the capture reaction induced by neutron and fission reaction and charged particle reaction. So going back to the uranium-5 fission cross-section, as you can imagine, in the year we perform a lot of measurement of this reaction using different detectors that were focused in different energy range of neutrons. So for example, if we take one of the 5 here listed, you can see here there are a couple of plots in which you can appreciate the good accuracy and the good resolution that we have with our measurement in our data. And several times, this is for example one of them, our cross-section are included in the general database and also in the IAEA standard database. So now we go back to the main topic of this talk. So what we want to measure, we want to measure the fission cross-section of uranium-235 in the high energy region. In a region in which we have no experimental data, so we decide to use a redundant approach. This is why here in this scheme you can see a lot of detectors. So we have 2 detectors. We use 2 detectors to measure the fission yield, so to measure the fission events coming from the uranium-5 sample. But in the meantime, since we are working with neutrons, we need some detector, we need something as reference in order to be able to measure the neutron flux that hits our U5 sample. In this energy range, since we are in this high energy parts, the main reaction reference that we can use is the neutron-proton elastic scattering cross-section. So this is just a scheme with the main feature of the different detectors used. So why we use two detectors to measure the fission yield? Because are two different detectors based in two different principles. One is the ionization chamber, for which we know really well the efficiency as a function of energy. And we know that this efficiency is really close to pi, so it's really close to 1. But this detector is able to work from the thermal energy point up to about 200 MeV, because above this energy, then there are several background reaction, that is difficult to discriminate this reaction with respect to the fission fragment events. And a parallel plate avalanche counter that in the other side is able to work in the whole energy region of N-TOF, so from thermal up to 1 GeV. The contra is that the efficiency is not 1, so it's smaller, is around 60%, and is also a bit more complicated to calculate it. For the neutron flux, we use 3 different detectors based in the same principle, and I will explain later better all the detail of them. So as I say, this is one of the 2 detectors used for the fission yield. The chamber is composed by 8 uranium-5 samples and 2 empty samples in order to measure the background events. And this is a radiography of the uranium-5 sample, because all these 8 samples were characterized using a radiography, exploiting the alpha coming from the sample itself. So all the samples were characterized. And this is an example of the events, so the amplitude of the events as a function of the neutron energy. Here in the top plot, as you can see, here are events coming from the uranium-5. So what is taking account this black line, that is our cut, to avoid to take the alpha, so all the background events, so not the fission fragment. We have all the fission fragment events. Here in the bottom plot, we have the same kind of plot, but taking account, as I say, the empty sample. So the sample in which we have not the U5 deposit. As you can see here, as I explained you, when we increase the energy, this means that we are seeing only the background. When we increase the energy, the background increase, and increase also in the amplitude itself. So it's not easy going higher to discriminate the fission fragment with respect to this kind of background coming from the aluminum that is in the chamber itself. And this is an example of the amplitude of the signal. In black points are the experimental data that are compared by Monte Carlo simulation, and for which we were able also to extract the efficiency of the chamber itself. The other detector that we used to measure the fission yield was the parallel plate avalanche counter, the PPAC. So in this detector, there were 2 uranium-5 samples and 3 PPACs. Each PPAC is composed by an anode and 2 cathodes. And as you can see here, the uranium-5 sample were placed in the middle of 2 PPAC in a kind of sandwich. This is because the basic principle behind this detector, is to detect the 2 fission fragments in coincidence. So here we have the uranium-5 sample. We expect 2 fission fragments, and we expect them back to back. So to recognize a fission events, we expect that to detect one fission fragment here and one fission fragment here. Imposing this coincident technique, we obtain this a plot that is kind of this one. So we have the amplitude in acquire with one of the two p-pack that are sandwiched with respect to the uranium-5 sample that we are studying. Respect to the time of the coincidence, so the window that we select in order to save only the events in coincidence. So all the events in the purple box are background events that, as you can see, are well separated with respect to the fission fragment events. And here in the orange box, we have another kind of background events that are the fission fragments coming from the other sample that are able to make a coincidence between all the p-packs inside the chamber. But as you can see, also in this case, this background events is well separate with respect to our main fission fragment events. So also in this case, we select the fission fragment and we obtain the fission yield for the two detectors that we used. As I say, in the same time, we have to measure the neutron flux. In this high energy region, we wanted to measure the neutron flux with respect to the neutron proton elastic scattering cross section that is our reference. So in perfect world, we would like to put a nitrogen sample and to put a detector to count the protons coming from this hydrogen sample. But to put a hydrogen sample is a bit complicated. This is why we decided to use a polyethylene sample placed in the neutron beam and to place a detector in a fixed angle with respect to the direction of the neutron beam. But this detector at this point has to be able to discriminate the different particles coming from the sample, because now if we have a polyethylene sample, we have the hydrogen that we want, but we have also the carbon. So the reaction of the neutron with carbon can generate different particles that at the final state we can have alpha, deuterium, protons, tritium. So we want something that is able to discriminate the different charge and the different type of particle that we can have at the end. A kind of detector that can do these things is a proton recoil telescope. This is a scheme of one of the 3 telescopes that we use. And this kind of detector is, in general, it has to be a fast detector and is based in the energy deposition of the particle interacting with the detector itself. So, for example, here we have 2 silicon detectors in front and 4 plastic scintillators that are assembled in the pyramidal shape, and the detector is at a fixed angle outside the direction of the neutron beam. How we can discriminate the different particles? The idea is to use the delta E matrix. So we select only the events that are in coincidence with 2 or more plastic scintillator, or between the 2 silicon detectors that are here in front. So if we select these events, we have energy deposition, for example, in this case, in the first plastic scintillator, and the total energy of the protons or the other particle that stops in the second scintillator, we have all the energy of the particle. So plotting the delta E versus the E, we have this kind of hyperbolas that, as you can see here, are proportional with the mass of the particle, of the interactive particle with the detector, and the charge. These are Monte Carlo simulation, and as you can see, if we have only hydrogen, we have in the end only one hyperbola that is coming from only protons that is picked in this energy region because it's a two-body reaction. And so the kinematics want that is like that. But when we put carbon in the neutron beam, you can see that we have the same hyperbolas from protons, but we have also the second one from neutrons. But as you can see, with this kind of matrix, we can discriminate the two different particles, and we can select only protons. That is what we want. This is another kind of proton recoil telescope. Is based in the same principle, and also in this case is composed by 3 plastic scintillators, and the idea is to select only the events that are able to produce coincidence between the 3. And this is an example. So if we select events that make coincidence between the 3 plastic scintillators, and we from the delta E matrix, we can select only the protons. And here, only the protons, you can see also here that also from the carbon, we can have protons in the final state. And this is why in this case, we can select the peak, as you can see here in this plot, the peak that is the blue one are the events generated with the interaction with the hydrogen that is in the sample. And the green events are the protons coming from the interaction between the neutron and the carbon. And in this case, I mean, the protons coming from the interaction with the carbon have a characteristic energy that is lower with respect to the protons coming from the neutron-proton elastic scattering. So, as I say, we can select only the protons coming from the polyethylene target, but as I show you right now, we can have protons also from the carbon itself. This is why during the measurement, we allocate some time in the measurement of the background, only the background coming from carbon. So instead of the polyethylene sample in beam, we put the carbon sample in beam. And in this case, selecting only protons, we are able to subtract the contribution of protons coming from carbon and to select only the events coming from the neutron-proton elastic scattering. We can do the same exercise using the Monte Carlo simulation, and from which we can define the efficiency of our system, and we extract the neutron flux. As I say, we use 3 different detectors, and as you can see here, this is the neutron flux extracted in the independent way with the green detector. We can call them RPTI and FN that are in red, and the detector from PTB that is here in blue. And as you can see here, I reported the ratio between the 2 detectors, and as you can see, we are in a good agreement without any scaling, without any normalization between the 2 systems. Since the energy region in which the system can work is a bit different, in the sense that the fission, the fission chamber, as I say, the ionization one is able to work until about 200 MeV, and also this detector, this telescope from PTB, is able to work until about 150 MeV. We decide to combine these 2 detectors together and the PPAC with the other 2 telescopes together, because with this combination we are able to reach higher energy. And in the region in which these 2 systems overlap. So from about 40 MeV to about 130 MeV, we extract the fission cross-section, also in this case, in completely independent way without any normalization or scaling. And also in this case, you can see that, I mean, we have a small fluctuation, but we are always within the 5% and within our uncertainty. So coming to the results, in blue, you can see here the final cross-section that we obtain with the weighting average of the two independent systems. And in this plot, I reported also the other two data sets that are available in literature, the Lisowski and the Nolte data, and the IIA evaluation, that is the main reference of the uranium, is the main evaluation of the fission cross-section of uranium-235, is the standard one. And below in the plot, you can see the ratio between the Lisowski data and the IIA evaluation with respect to this work, to our result. Now, with this setup, we were able to go higher in energy. We were able to reach 130 MeV. And as I said, there are the first experimental data in this high energy region. This plot is just to show you that I reported only a few of them. I took some models calculation just to show you how many there are. And also, if you change a bit the parameter, you can obtain really different value for the cross-section. So this is why more data are really needed at this point. So in this case, I select only two of them. Here in blue, you can see the default parameter, means that we took a general model to evaluate the fission cross-section using the default parameter, which is that are standard right now in order to simulate or to reproduce the fission cross-section itself. As you can see here, the blue parameters are really always below our experimental data. And with our experimental data, we are able to define a better set of parameters that are able to follow better our trend and our scale in the fission cross-section value. Another important thing that we can do, and we did with our experimental results, is to do a comparison between the neutron-induced fission cross-section with the proton-induced fission cross-section that are reported here, the two of them. A really important point in order to have a good theoretical calculation of the process is to be able, with the same set of parameters, to reproduce the level and the shape of both of them. As you can see here, the default parameters were super nice for the proton-induced fission cross-section of uranium-235 because were the only data that were available in order to define the model. But as I already described you, are not good for our results. But if we play a bit with the level of the barrier and the density, the level density, we are able to reproduce simultaneously in a good way both of them. And this is important to underline the reasonability of our results and how can play a role in the theoretical model for the fission cross-section itself. So with this, I came to the conclusion and just to tell you that this was the first neutron-induced fission cross-section measurement of uranium-235 in this high energy region. And was also the first time in which we measured the neutron flux itself at NTOF. And I think I show you that our data, since we use this redundant approach, have a good accuracy, and we prove the reliability of the results. But we don't want to stop here. We don't want to go. We want to go higher in energy in order to fix and to define better the things for the model and for the fish and for the theoretical point itself. So this is why we are planning to develop a new detector that is able to reach 1 GeV of neutron energy, and possibility to measure not only the fission cross-section, but also the fission fragment angular distribution. That is another important things that we will get to measure simultaneously to the cross-section itself. And with this, I thank you for your attention.